Hello, I'm Pranav and my topic is clock synchronization in distributed computing. So let's get started. So in a distributed system, we've got multiple computers, often in different locations, trying to work together on shared tasks. The tricky part is they all have their own internal clocks. Now the problem is those clocks don't exactly run the same. They might be a few milliseconds fast, some slow. So over time, those small differences add up and lead to something called clock drift. So basically, clock synchronization is the technique we use to fix that drift. We want all those nodes to either agree on a common time or at least maintain a consistent order of events. That's what helps to keep the distributed system running smoothly. Okay, so why does this matter so much? Let me give you a few real life examples. Let's say we are using a distributed database. If, for example, let's say two users try to update a record at nearly the same time, the database needs to know which one came first. If the clocks aren't in sync, the system might overwrite the newer data with the older data just because the timestamps are wrong. Or now let's example another scenario where we are debugging a bug that shows up in a log across different machines. The logs aren't timestamped properly, so we won't be able to reconstruct what actually happened. So yeah, synchronizing time across machines is kind of the glue that keeps the entire system consistent and reliable. So when we talk about clocks in distributed systems, we are not just talking about the time in the traditional sense. There are two main categories, physical and logical. Physical clocks are what we are all used to, like real world clocks like UTC time. These are useful when you want your system to be in sync with the outside world. But sometimes real world time doesn't matter. What matters is the sequence of events. That's where logical clocks comes in. Logical clocks don't just tell you about something, for example, that happened at 3 p.m. They just tell you that event A happened before event B. That's really useful in scenarios where we care more about causality rather than the actual timestamps. So, here's the simple breakdown. Physical clocks represent actual time. You need to sync them regularly using protocols like NTP. Logical clocks are about the order of events. They don't need any external references. If you are building something like, for example, a log analysis system or a distributed event scheduler, physical clocks would make more sense. But if you're just trying to track the flow of messages or operations inside the system, logical clocks would be a simpler approach or they might be more effective. Now let's discuss different algorithms used in clock synchronization. Let's start with Christian's algorithm. Christian's algorithm is one of the earlier methods used for clock synchronization and it's pretty easy to understand. Let's see how it works. A client sends a request to a time server saying like, hey, what's the time? The server responds with its current time. Now the client it doesn't just accept the time value as it is. It measures how long the round trip time took and adds half of that delay to the time it received. So, for example, let's say it took 100 milliseconds to get the reply. The client assumes 50 milliseconds of delay each way and adjusts the time accordingly. This works well in if the network is stable and the delays are symmetrical. But if the network is busy, where delays are unpredictable, it can be a bit inaccurate. Now let's get to Berkeley's algorithm, which takes a different route. It's more like a group project. One machine called the master or coordinator asks all the other machines, hey, what's the time for you? So each one replies with their current clock time. The coordinator calculates the average of all those times, including its own, after removing any outliers that might seem off, and then sends back the adjustments to, for example, node 1, like add 20 milliseconds to your time, or to node 2 to subtract 15 milliseconds from its time. So instead of syncing to a single external clock, they just sync to each other. It's especially useful in systems where internal consistency is more important than syncing with the real world. Now let's move over to Network Time Protocol (NTP). NTP is the protocol the internet relies on for time syncing. It's incredibly powerful and smart. It works on a hierarchy of servers called strata. NTP uses a client server model and a peer to peer model to exchange time information and adjust clocks. So at strata 0, you have super precise clocks like atomic clocks or GPS devices. Strata 1 follows Strata 0, and Strata 2 servers are connected to Strata 1 servers, and so on. So NTP uses multiple time sources and calculates round trip delays, offsets, and jitters. It doesn't just one answer. It applies statistical filtering to choose the best. That's why it's the most popular approach. Now let's move over to Lamport logical clocks. Lamport clocks gives us a really simple way to order events in a distributed system. Each process has a counter. Before any event, it increases the counter by 1. When it sends the message, it includes that number. When the receiver gets the message, it updates its own counter to be 1 more than the max of the own value and the messenger's timestamp. The beauty here is that event A happened before event B. Lampord's clock ensures A's timestamp to be smaller than B's. But there's a catch. They can't detect two events that are concurrent, meaning that they happened independently. Here's then This is where vector clocks come in. Instead of just a single counter, each process keeps a vector, basically a list, where each element tracks the count for every process in the system. When sending a message, the process includes this vector. The receiver compares its vector with the one it just got, element by element, and updates it to keep the max of each element. Then it bumps up its own entry. Lastly, we've got a channel unpod algorithm. It helps you to take a snapshot of the entire system without stopping it. Let's say one process initiates the snapshot. It records its own state and sends the marker message down all its communication channels. Any process that gets that marker for the first time also records its state and sends markers out. They also record any messages that they receive before they get the marker, because those are a part of the system state at that point. So by the end, every process has a record of its own state and what messages were in transit. So yeah, that's it from my side. Thank you.